In this lesson, we're going to talk about graphs and how they tell a story. So the first thing we'll discuss is how can a line graph actually tell a story, and then we'll look at some examples. How can a line graph tell a story? A line graph uses segments to show how data values change over time. And line graphs allow you to see trends and patterns in data and can show you how one variable affects the other. For example, a line graph can provide information about how something changes over time, where time in minutes is represented along the x-axis and the variable that changes over time, such as speed or altitude, the height of a plane, money in a bank account, temperature outside, that would be on the y-axis. This graph shows the speed of an antique auto ride at the fair. It shows that the car increased in speed for a short period of time, and then it moved at a constant speed for a slightly longer period of time. Then the car slowed down quickly for a short amount of time and traveled at a slower speed for a period of time. Next, the car sped up to go faster and then traveled at a constant speed for some time, and then finally the car slowed to a stop and the riders got off. A couple of things to note here is that it's important when reading a graph's story to look at what's on the y-axis here and what's on the x-axis. So this is speed. So you can see that this line is going up. So you have to think about what does that mean for the speed to be going up? Well, that means they're getting faster in this case. And when the line is horizontal, it doesn't mean they're stopped because this is speed, not distance. If this was distance and it was stopped, that would mean the car is actually stopped. But for speed, when it's flat like this, it doesn't mean they're stopped. It means they're going a constant speed. They're going maybe 3 miles an hour in the antique auto. And then they're slowing down, and then they're going a constant speed. And then they're speeding up, and then they're going a constant speed, and then they slow down. So it's really important to focus on that y-axis and what you're measuring here. Horizontal segments represent a constant speed in this case over time. Segments with a positive slope represent an increase in the car's speed, or whatever's on the y-axis, whatever we're measuring. And then segments with a negative slope represent a decrease in the car's speed over time. When you look at a line graph, ask yourself what the story of the data in each section are telling you. A flat or horizontal line segment, just like I said before, means there is no change in whatever you're measuring. A slope that increases or goes up from left to right shows an increase in whatever unit you're measuring, and a slope that goes down from left to right is decreasing, which represents a decrease in the unit of measure. Before we look at a few examples, let's talk about two more vocabulary words. An independent variable is a variable that stands alone. It is independent, and it isn't changed by the other variables that you are measuring. For example, someone's age might be an independent variable. Other factors, such as what they eat, how they go to school, how much television they watch, those aren't going to change a person's age. So a person's age is independent. In fact, most of the time as a measurement is an independent variable. The independent variable will go on the x-axis. That's the horizontal axis that goes this way on the graph. A dependent variable depends on other factors. That's why it's dependent. For example, a test score could be dependent variable because it could change depending on several factors, such as how much you studied, how much sleep you got the night before you took the test, or even how hungry you were when you took it. So a test score could be a dependent variable. In contrast to the independent variable, the dependent variable is on the y-axis. The y-axis shows a range of variables for which the data might be collected. Some examples of things that might be on the y-axis might be speed, altitude of a plane, money in a bank account, temperature, essentially any measure that might be expected to change over time. Let's look at a few examples. Example number 1. This is a graph that represents the motion of two of the Clydesdales racing at the fair as they approach and go around the state fair track. What story does the graph tell? Maybe take a pause here and take a look at the graph. Some things you might want to consider is what happens at the start. Why do these two things start at different places? Perhaps this Clydesdale at time 0, they already started 600 meters down the track. And this Clydesdale didn't start. Maybe it needed a little bit of a kick to get it going because it didn't start the race until 1 minute in. Do you see that? This one started right away, but it also started 600 meters down the track. This one waited a minute before starting, but then got going. The next question here is, why do you think the graph almost levels off for the same amount of time for both Clydesdales? You see here, it levels off. What happens at that leveling off? If you thought about the fact that they're going around a bend, maybe they're going around the circle, and this is where they're going around the circle. They got to slow down a little bit to go around the circle. That's probably what happened here. And then the last question, who won the race? So we're making the assumption that the race is 3,200 meters long. Who won the race? Well, the first Clydesdale, this Clydesdale here on the top, finished it in 10 minutes, and this one finished it in 12 minutes. So this Clydesdale would have won this race. Let's take a look at one more example. This is a graph of a balloon being blown up for the dartboard at the fair. What's the story? So in my mind, I start asking myself some questions. Why does it level off here every so often? Why does it decrease at the end? Why does it start here at 3 inches? Why doesn't it start down at 0? Can you answer some of those questions? Well, a balloon has some length to start with, right? When you first start blowing up a balloon, it's already a certain length, even without any air being blown into it. And then usually people blow into the balloon, and so it gets bigger, and then they have to take a breath. And that's what this flat line would represent, that the change in length is not changing. The amount of length is not changing at all here from 2 to 3 seconds. So he's probably taking a breath and holding on to the end of the balloon so it doesn't let go. And then doesn't take quite as big a breath for the next couple of seconds because that's not as long as this one. And then it has to take a bigger breath and then blow into the balloon. And then about the same length of breath and then blow into the balloon a little bit. I think he's running out of air, or perhaps the balloon is not getting bigger as fast because it's gotten so big and blown up that it's not changing as much. And then what happens here? The person blowing up the balloon let go of it and it let out all of the air that was in there. So that's some examples of how you can read a graph and come up with a potential story that matches it.